So the last point I want to make is about how to use oxidation states to determine whether your species is oxidized or reduced. So remember that one of the things we talked about earlier was that it's difficult to know whether your species is oxidized or reduced if you're just looking at charges, right? Standard charges, because in covalent compounds, those electrons are shared. However, once you know the oxidation number, it's pretty easy to tell. The species that's oxidized is going to lose electrons. Okay, so if it's losing electrons, that means that its oxidation number should become more positive or less negative, either way you think about it, because electrons are negatively charged. So if you lose electrons, your oxidation number will be less negative. And so you expect an increase then in oxidation number for things that are oxidized. So let's say it goes from -5 to -2. That means that species is oxidized. Or it goes from 0 to +5. That species is oxidized. Reduction means that you're gaining electrons, so that means your oxidation number will become more negative. So there's a decrease in oxidation number. So again, for example, you go from -1 to -3, that's a reduction. Or you go from +5 to +2, that's also a reduction. Let me work through a couple examples here to show you how to put this in practice.
We can use the concept of oxidation states to help us determine which species is oxidized, reduced, and what's the oxidizing and reducing agent. The way we do that is first we select one of these reactions. So let me just pick reaction number 2 here that has all these species in here. And the first step we do is to figure out, I'm just going to rewrite the reaction here. First step is to figure out what the oxidation state is for each of the species, of the element, I should say. So starting with H2O. Now this, again, you hopefully at this point you're either memorize or remember enough of the list of rules of determining oxidation state, but with hydrogen and oxygen together, hydrogen is assigned first as +1, and there's 2 of these, so it's +2. That means the oxygen has to be -2. Aluminum is a free element, so it's going to have an oxidation state of 0. Manganese and oxygen. Well, manganese is a metal, but it has multiple charges, so unless we figure out the oxygen first, we can't tell what the manganese would be. So we start with oxygen being -2, which means this is -8, and so manganese must be +7 to balance that out. Aluminum hydroxide, this is an ion, a complex ion, but the way we can determine this is we just start again with aluminum, the standard charge is +3, and then oxygen, hydrogen, again +1, -2, so no change there. And then the manganese at the end here is going to be -2, and then we have -4 obviously on this side, and then that causes us to give +4 for the manganese in manganese oxide. Okay, so now that we have that, what we need to do is figure out which elements have a change in oxidation number. So if I look here, my hydrogen, my oxygens actually stay exactly the same. So that means that nothing happens to them. And that's okay. Not everything has to be oxidized or reduced in a redox reaction. Water really just serves as a solvent in this case to allow those ions to form. So let's take a look at this species where an actual change occurs. Aluminum is 1. I notice that I have an oxidation number of 0 in the reactant side and it becomes +3 in the product side. So that means there's an increase, right? So increase means oxidation has occurred on aluminum, because that means you've lost some electrons. For that element to become more positive in its oxidation number, it has to lose some electrons. Let's take a look at any other element that has a change in oxidation number, and we notice that manganese is the other element that has a change. So manganese goes from +7 to +4. So that means there's a decrease in oxidation number, and that would mean that there's a reduction occurring for manganese. So then what we can say is that aluminum is oxidized and manganese is reduced. Now what about the oxidizing and the reducing agent? Remember that those are reactants that's an agent. So an agent is something that's causing something to happen. So an oxidizing agent is the reactant that causes things to be oxidized, but that agent itself is reduced, right, or contains the elements that's reduced. So that means that manganese, the compound that contains manganese is the permanganate ion. So the permanganate ion is the oxidizing agent in this case, okay? And then if you look at the reducing agent, well, aluminum is the element that's oxidized, but aluminum is also the reactant itself. So therefore, aluminum is the reducing agent.
So the issue with redox reactions reaction is that in order for electrons to be transferred, the redox reaction must occur in aqueous solutions that contain ions. So in other words, some type of an electrolyte. Most of the time, it's not as easy as just looking at the equation to balance it. So for example, if you look at this equation right here, aluminum and silver ion going to aluminum ion and silver, you might look at that, and based on our ability to balance so far, which is just looking at number of elements and making sure that they're correct, that might look like a balance equation because you have one of each of the element. But the key here is to understand that those elements are not existing in the same state. So the aluminum here is a solid and the aluminum here is an ion. So you're going to have to worry not just about the element number, but also how many electrons are existing on the left side of the equation versus the right side of the equation. And that's where we need more advanced method of balancing equations, which is called the half-reaction method. So the first thing you do when you have an equation like this is you identify which species is oxidized and which species is reduced. Now remember, oxidation is an increase in oxidation state. So that means you're going to have to assign the oxidation state for all of the species first. So aluminum would be 0. This silver ion would be +1, that one would be +3, and then the silver element would be 0. And so we can see that the aluminum is oxidized because it goes from 0 to +3, and then the silver is reduced because it goes from +1 to 0. So that's our first step. Once we identify that, we separate them out into half reactions. The first half reaction is the oxidation half reaction, where aluminum goes to aluminum 3+, and there should not be a positive sign there. This should just be aluminum 3+ AQ. And then reduction is the silver ion going to the silver solid. Now, once we have that, what we have to do is then add the electrons to balance out the charges. And the way we do that is the following. Each electron is worth -1. So what we're trying to do here is we look at the left side and the right side to determine what kind of charge we have. So on the left side, our charge currently is 0 because aluminum is 3 elements, so that has an oxidation state of 0. Aluminum 3+ has an oxidation state of +3. So we have a 0, we have a +3. We can add -1s to one side or the other to make them balance. So it seems like the reasonable thing to do is to add 3 -1 on the right side, so that when you add that plus the +3, you get 0, which is equal to the left side. And so that's what we do here. We add 3 electrons. Once we add the 3 electrons, that balances out the charges on both sides. If you look at the silver is +1 on the left side, 0 on the right side. So that means adding 1 electron, which is -1, would make this side become 0 in total. And then that would equal to the right side. One point I want to clarify here is that it doesn't necessarily always have to be zeros on both sides. Sometimes it's +2 on both sides. Sometimes it's -1 on both sides. In this specific example, it happens to be 0 on both sides. Once you have the electrons, your equation now look like this. Your half reactions look like this. What you need to do is you need to equalize your electrons, because you have to have conservation of charges, just like you have to have conservation of mass. So in this case, to balance out the electrons, I'm going to have to multiply the electrons at the bottom by 3, and the top one will just remain like that because it's already 3. So that's what I'm doing here. I have the top equation looking the same. The bottom equation is 3 times the starting equation. And then I multiply that across, so that means I have 3 electrons, 3 silver ion, and 3 silver element. After that, I'm going to add the 2 reactions back together. So here's aluminum going to that, right? Aluminum ion, 3 electrons, and then here's the equation that I just multiplied in, and I add the 2 of these together. This is what I end up getting, okay? And so that is your balance equation. Now, the way you can tell that it's the balance equation is because if you look at the elements, there's 1 aluminum, there's also 1 aluminum here, there's 3 silver, and there's also 3 silver here. But in addition, you also want to check the charges. So aluminum is 0, silver is +1 and there's 3 silver, so it's going to be +3. So the entire charge on the left side is +3. You go to the right side, the aluminum ion is +3. The silver element is 0, so 3 times 0 is still 0. So overall you have a charge of +3 on the right side. That means you have +3 and +3, so they're equal as well. So that means both the charge and the elements are equal to each other. That's unlike when we started with this equation, right? If you look at this one, you can see that the left side, even though the number of elements are the same on both sides, but the charge on the left side is only +1 and the charge on the right side is +3. So that's how we know that that equation is not balanced.
Okay, let's see if we can apply the rules that we just learned about balancing redox equations on this particular equation. Now, if you look at the number of elements here, you might think that the equation is balanced because you have one of each of the elements on the reactant side and on the product side. But if you actually look at the charges, which is important for redox reactions, you'll find that on the left side right now, the total charge is +1 because the copper is +1 and the iron is 0. And then on the right side is +3 because the iron is 3 and then the copper is 0. So that's the indication that the equation is not yet balanced. And so you have to use those rules that we talked about earlier to help us determine the balance equation that's correct. First, we start with using the oxidation numbers to help us determine what's oxidized and what's reduced. Copper here is +1, iron is 0, and then iron 3 is +3, and then copper here is 0. So what we do then is we determine that for the iron it's been oxidized, and for the copper it's been reduced due to the change in the oxidation numbers. So then we're going to write our oxidation half reaction, and that's going to be just Fe going to Fe3 plus, and then our reduction half reaction is going to be copper plus to copper. And then what we do is we balance each of the half reaction. If you look at the oxidation half reaction, to make both sides have equal charge, I'm going to have to add 3 electrons. That's going to cancel out that 3 plus to give us a total of 0 on the right side, which matches the one on the left side. And then for the reduction half reaction with the copper, I'm going to need to add 1 electron to again balance out the left side with the right side in terms of charges. Once we balance them out, we notice that the number of electrons are not equal to each other, so we're going to equalize the electrons by multiplying the bottom equation by 3, since it only has 1 electron right now, and then the top one just multiply by 1. So mathematically this is the same as finding the lowest common multiple of the number of electrons. And then once you do that, you can add them together. So the reactant side would look like the following: iron plus 3 times 1 electron here is going to give us 3 electrons, and then 3 times the copper plus is going to give us 3 copper plus. Just don't forget the charges in these redox type balancing, because once you forget that, there's going to be a mistake later on in the balance equation. On the product side, we have Fe3 plus 3 electrons plus 3 copper. You cancel out the species that are the same, which if you've done this correctly should be the electrons. And so your final balance equation would be Fe plus 3 copper plus going to Fe3 plus 3 copper. Now, if you compare and check the balance equation, you notice that they both have 1 iron on either side, 3 coppers on either side, and the total charge in both cases are +3. So we have +3 here because we have iron being 0 and copper being +1, but there's 3 of them, so it's +3. On the right side, we also have +3 because iron is +3 and copper is 0, so 3 times 0 is still equal to 0. So then that equation is balanced.